I've given probably 400 and some talks in my career, and I've never been late for one until today. And so thanks for running behind. Actually, technically wasn't late, I guess. By the way, that's not a laser. That's a laser. Okay. I run a research lab here on campus where we do optical remote sensing. So that's what I'm going to talk to you about today. And everything we do is sort of focused around studying the natural world with optical devices that you can think of as cameras or really fancy cameras, all the way to laser systems and whatever we can dream up. This is a photograph that I took of the Aurora Borealis from an airplane coming home from Alaska. And so that's one of the more challenging photographic assignments I've ever had. Here's myself, a colleague from Germany, and Paul Nugent, who's a PhD student in my lab, in my front yard 2 summers ago. And you know what we're doing? Who recognizes what we're doing? We are playing. Do you ever take time to play? So we have big budgets and fancy projects with big deliverables and goals. And every once in a while, you just have to set that all aside and play. And even when we've got the big budgets and the fancy instruments, we're basically playing, but just don't tell anybody that. So what we're doing here is we have a little tiny thermal camera, and it's embedded inside of a fairly small telescope. And that allowed us to take pictures of thermal images of things far away and get a fairly close-up picture. And so we thought, first thing that came to our mind was, let's look at the moon. And so, oh, I forgot, I need to tell you this. What we do in my lab is we design, build, and calibrate optical sensor systems. That's the engineering part. I'm in the College of Engineering, so I'm supposed to do engineering once in a while. But my degree is in optical sciences, and so I think a little bit more like a scientist. And so I do the engineering to enable the science, and the science is to study whatever it is about nature that we happen to be studying. And the pictures I'm going to show you today illustrate 3 or 4 of those things that we've done. So the first thing we did when we had that thermal camera mounted in the telescope is we pointed it at the moon. That's not a thermal image, that's a picture out of my out of my visible digital camera. And here's what the moon looks like in the thermal infrared at the same time, same night. And so this is scale on the vertical in temperature, that's degrees Celsius. So you can see that if you were on the sunlit side of the moon, it would be a very hot place. You'd find this to be a little too warm for your liking, almost no matter who you are. 400 degrees C would basically melt you. And that's because they have no atmosphere. The moon has no atmosphere, so it gets excruciatingly hot in the day and excruciatingly cold in the night. And we might feel like we get excruciatingly hot or cold, but believe me, compared to that, we don't do either. The infrared cameras that we were using, the methodology that enabled that playing is the methodology that we developed to do hardcore science. And the science is studying clouds in the Arctic. This is one of the biggest uncertainties in current understanding of climate. And so in the Arctic especially, clouds are very hard to measure. Satellites basically cannot do it. And we have to do it from the ground. And so we've developed a method to use these small infrared cameras in this box looking up to measure clouds for the purpose of climate modeling. So this is at the very northern tip of Alaska. Another experiment we did was in Hawaii. This is with an all-sky polarization imager. So this is like a scientific grade camera here, a whole bunch of custom optics, and then a fisheye lens. And all that system was designed and built here at MSU by myself and Nathan Poost here, a PhD student who was working with me. And we were up on the top of the volcanic mountain called Mauna Loa. If you've been on the big island of Hawaii, you may know this place. It's very interesting because it looks like being on the moon. It's not the moon. This is what an all-sky image looks like in the visible, and this is on a day with no clouds. The sun is down here. This is what the same kind of scene looks like with our polarization imager. And what it's showing you is Blue means the light is not polarized, and red means that it's polarized a lot, and everything in between is in between. And so this sky has a pattern, even though you can't see it with your eye, it has a pattern where the electric field is vibrating in a very specific direction in this band across the sky, located 90 degrees from wherever the sun is. And so that will move across the sky as the day progresses. Some insects and some birds use this pattern for navigation. It's even hypothesized that some early mariners used this for navigation. We also do laser remote sensing. This is a picture of our LiDAR system, light detection and ranging system, in Cobley Hall just across the way. Outside, what you see, if you're close to it, is a laser beam going up. In this case, we're probing that cloud to understand why those colored rings can appear when classical meteorology tells us that they can't. And then what we just flew just a couple days ago was a laser system in this small Cessna aircraft looking down this time into the waters of Yellowstone Lake to map out the possible spawning locations of invasive lake trout. And when we did this before as a pilot study, I'm sorry, this is kind of gruesome, it comes shortly before lunch, but this illustrates the problem. This is the invasive lake trout. These are baby cutthroat trouts. Trout. If you want to kill off a population, the best way to do it is to kill off the young people, or the young whatever. And in this case, they're killing off the young cutthroat trout, and so the population is in danger, and that would unsettle the entire Yellowstone ecosystem. So there's a lot of interest in trying to do this actively. And with that, I will just encourage you to come play with us if you have any interest. Thank you very much.